Today we're going to look at camming. So here's an example of a camshaft. This would be the master rotating at some speed, and the camming device which actuates the slave based on its profile. The important thing about camming is the slave follows the master no matter like its speed or variation in speed. The slaves are synchronized to the master over time. So we're going to take a look at the Copley camming user guide on the download page. Under software documents, we get the camming guide. This will have the basic overview diagram of a cam function. So we'll take a look at that. So you have a master putting its input pulses in, or you have an internal master at a set frequency, or you can change the frequency. You get a trigger to initiate the camming. You can offset the cam table. You have a table which we follow. The drive will interpolate between positions and command the position of the slave. So the only thing we really have to worry about here is the creation of the cam table. It's important what the cam table looks like because we are doing interpolation between points. So it's not a good idea to set your master count as 1, 2, 3, 4, and then your slave, because we can do interpolation. So add a little space. So go 0, 10, 20, and then in between those positions, we'll do interpolation and close the position loop every 333 or 250 microseconds based on the drive. Now, today, as an example of a camming, we're going to take a look at this company, Stelron, who's been into camming since the 1960s. These guys are experts at creating the cam tables for their camming equipment. And there's a device here that we're going to look at, which has 2 linear actuators and 2 cam tables on a 2-axis drive to do the pick-and-place action at the output. So the linear motors are defined by some sinusoidal and some point-to-point moves over time. That's the cam table. And the master will just be a set run of clock pulses. So we'll take a look at the cam table for this device. And we have an A and a B axes on the BE2 or the BP2. 1 drive to drive 2 motors. Let's take a look at the device here. So we have a servo tube motor with a magnet and the coil, 2 motors. There's some mechanical bearings here. And as the position changes of the motor, you get a change in the output. And you can move them together or define any motion. But the linear motion of the pick-and-place head is what we're striving for. So we got the BE2 with feedback devices, sine, cosine from the motor interpolated, does the position control. The stow, I got the serial cable connected here, and we can program the drive, tune the position loop, and then enter the cam table. So the Stelron guys have provided the cam table. Here's the master positions and then the slave positions to execute the position. There's a cam table for A and then a cam table for B. So we'll look at A. Now the cam configuration can have internal count frequency. This I've made a variable in the indexer program. Input 2, I made it edge triggered. We're going to use cam table 0. You can have up to 10 cam tables, different cam tables. And again, the CVM takes control on startup. We're going to use the CVM Indexer program to do the homing. So let's take a look at the CVM program here and see what we did. So sequence 0 is going to wait for a second, which is a good idea when a program starts running. Let it power up. It disables the A axis. It homes to a hard stop on B. It homes to a hard stop on A. Makes a little adjustment move on B. Waits for a time delay, and then jumps to sequence 1, step 1. Now, we could use Indexer register to select the sequence. Bit 15 makes it go, and 0 at the lower order byte is for sequence 0. Or we could select sequence 1 using register 0. But in this case, it's use immediate startup on go, so the thing will home right away and then jump to sequence 1. Now my modification is I'm going to use R1 to set the frequency of the cam table so I can test different rates. I'm going to start off by setting R1 to 0. After power up or reset, R1 will always be equal to 0, but then we can set it over the ASCII interface. But it's just going to loop here until it's something other than 0, and then it enters in, and it sets the counts per second in units of 0.1, because I've got a variable R1. Edge triggered cam table 0 for axis A. Same thing for B. And then I'm going to set R1 back to 0, so I can wait and do this all over again, jumping back up to sequence 1, step 1. So we can let this run and watch to see what it does. So there's the homing of the A axis, little offset, homing of the B axis. And now that both axes are homed, we're ready to start making the move. So let's set the value of R1 to set the rate. So we'll use tools as the command line, I command R1, and we can set it to, well, initially we had 3,000, but that's the frequency, but in units of 0.1 it's 30,000. And then to make it go, we're going to use the edge trigger to initiate the move, but I also want to use the scope to take a look to see what happens over time. So that was the move. And we're looking at the profile velocity in pink, and then B in blue. And you can see it's a sinusoidal move, and there's actual current during the motion. So we can take a look at this profile here and see what our current is. The RMS current of this move for both the axis A and axis B is less than the drive's continuous current. As long as we're less than the continuous current, we can do this all day. So perhaps we can increase the rate a little bit and get a shorter time. So let's take a look at the motion here, because it's cool. So that was a very high speed move. So we got the new trace. It took a lot less time to make the move. Our continuous current is still less than 3 amps. Perhaps we could go a little bit faster, but we have to be careful that we don't go too fast. Okay, there's the duty cycle, reading trace data. So that one move consumes pretty close to the limit, so we'll have to be careful. You know, monitor that over time, make sure that we don't exceed the current limit. But this brings the cycle time below, well, 0.8 seconds. So 0.1 seconds. Then we scope trace to 0.9, so 0.8, 800 milliseconds. Good trace time. So we're going to talk a minute about the cam tables. Again, the cam table is a file. We can get a file from Stelron for their device and load it in, and then save it to flash, and then the CVM can run it at different rates. So we can save a cam table. It's a CCT file. So we're looking at the cam tables. Here's the Stelron. let's open this with, so I'm just looking at this file with Notepad. It's just basically 2 columns and some cam information here. And that's really all we need for the cam table. So we can receive a new cam table, we can open it up, and then save to flash. And that could be a new cam table. We could create a new cam table. So these are all in the flash of the drive. But as I wanted to show you, it's also possible to do this this cam table in the RAM. So we have an extra minute. Let's take a look at that. So we have an app note here that talks about camming and the format of the cam table. And then there's the cam tables into the flash. This uses the same flash as the CVM Indexer. So there's some file management. I mean, this is some real complicated stuff. We don't have an example of it. CME2 is the only thing that does it right now. But this is a document that describes the function of the loading cam tables into the flash. But it doesn't make sense to develop your own software to do that when CME2 can be used to load the cam tables. But what we did once upon a time is develop cam in the RAM over CAN, and I think a little CML program was used to get this to load and unload. So there's some file management that goes on, and you load the cam tables over the CAN interface into the RAM and execute them from RAM. That's a compression format too. But again, at this time I do not have an example of this, and that would be a separate thing. All right, well, thanks for your time, and let's watch this thing move one more time. Camming, very cool.